Our next lesson is on estimating with confidence, estimating a population proportion. In this section, we'll look at constructing and interpreting a confidence interval for a population proportion, determining the sample size required to obtain a level C confidence interval, and describing how the margin of error changes with sample size and level of confidence C. Let's say your teacher has a full container of different colored beads. Your goal is to estimate the actual proportion of red beads in the container. You form 3 or 4 students in a team and determine how to use a cup to get a simple random sample of beads from the container. Each team then collects one simple random sample of beads. You determine a point estimate for the unknown population proportion. You then find a 90% confidence interval from the parameter P, and consider conditions required for the methods you used, and then compare your results with the rest of the class. Suppose a simple random sample of beads resulted in 107 red beads and 144 beads of another color. The point estimate for the unknown proportion P of red beads in the population would be P hat equals 107 out of 251, or 0.426. How can we use this information to find a confidence interval for P? If the sample size is large enough that both NP and N1 minus P are at least 10, the sampling distribution of P hat is approximately normal. The mean of the sampling distribution of P hat is P, and the standard deviation of the sampling distribution is sigma P hat equals square root of P times 1 minus P all over N. In practice, we do not know the value of P. If we did, we would not need to construct a confidence interval for it. In large samples, P hat will be close to P, so we replace P with P hat and check in the normal condition. Check the conditions for estimating P from our sample. Is it random? The class took a simple random sample of 251 beads from the container. Is it normal? Both NP and N times 1 minus P must be greater than 10. Since we don't know P, we check the counts of successes, red beads, and failures are both greater than or equal to 10. Independent. Since the class sampled without replacement, do they need to check the 10% condition? At least 2,510 beads need to be in the population. The teacher reveals there are 3,000 beads in the container, so the condition is satisfied. Since all 3 conditions are met, it is safe to construct a confidence interval. We use the general formula from section 8.1 to construct a confidence interval from an unknown population proportion P. The sample proportion P hat is the statistic we use to estimate P. When the independent condition is met, the standard deviation of the sampling distribution is given using our formula. Since we don't know P, we replace it with the sample proportion P hat. This gives us what's called the standard error of the sample proportion. When the standard deviation of a statistic is estimated from data, the result is called the standard error of the statistic. How do we find the critical value for our confidence interval? If the normal condition is met, we use a normal curve. To find a level C confidence interval, we need to catch the central area C under the standard normal curve. Z star indicates a critical value rather than a standardized score calculated from the data. For example, to find a 95% confidence interval, we use a critical value of 2 based on the 68, 95, 99.7 rule. Using Table A or a calculator, we can get a more accurate critical value. Note, the critical value Z star is actually 1.96 for a 95% confidence level. We use Table A to find the critical value Z star for an 80% confidence interval, assuming the normal condition is met. Since we want to capture the central 80% of the standard normal distribution, we leave out 20% or 10% on each tail. Search Table A to find the point C star with area 0.1 to its left. The closest entry is Z equals negative 1.28. So the critical value Z star for an 80% confidence interval is Z star equals 1.28. Use Table A to find the critical value z star for a 96% confidence interval. Assume that the normal condition is met. For a 96% confidence interval, we need to capture the middle 96% of the standard normal distribution. This leaves out 2% on each tail, so we want to find the z-score with an area of 0.02 to the left. The closest entry is z equals negative 2.05, so the critical value for z star is 2.05. Once we find the critical value, z star, our confidence interval for the population proportion is statistic plus or minus critical value times standard deviation of statistic. In our case, it will be p hat plus or minus z star times the standard deviation. Choose a simple random sample of size n from a large population that contains an unknown proportion p of successes. An appropriate level C confidence interval for p is given by the same formula we just looked at above up here, where z star is the critical value for the standard normal curve with area C between negative z star and z star. Use this interval only when the number of successes and failures in the samples are both at least 10 and the population is at least 10 times as large as the sample. Calculate and interpret a 90% confidence interval for the proportion of red beads in the container. Your teacher claims 50% of the beads are red. Use your interval to comment on the claim. We checked the conditions earlier. For a 90% confidence level, we use z star equals 1.645. We calculate and compute 0.426 sample proportion plus or minus 1.645, which is z star, times the standard deviation. 0.426 times 1 minus 0.426 all over 251 under the square root sign. We get a confidence interval of 0.375 and 0.477. We are 90% confident the interval from 0.375 to 0.477 captures the actual proportion of red beads in the container. Since the interval gives a range of plausible values for p, and 0.5 is not contained in the interval, we have reason to doubt the claim. We can use the familiar four-step process whenever a problem asks us to construct and interpret a confidence interval. What parameter do you want to estimate and at what confidence level? Identify the appropriate inference method. Check conditions. If the conditions are met, perform calculations and interpret your interval in the context of the problem. That is our state, plan, do, and conclude four-step process. In planning a study, we want to choose a sample size that allows us to estimate a population proportion within a given margin of error. The margin of error is in the confidence level is the part of the formula that's the z star times the standard deviation. Z star is the standard normal critical value for the level of confidence we want. Because the margin of error involves the sample proportion p hat, we have to guess the latter value when choosing n. There are two ways to do this. Use a guess for p hat based on past experience or a pilot study. Use p hat equals 0.5 as the guess margin of error is largest when p hat equals 0.5. To determine the sample size n that will yield a level C confidence interval for a population proportion with maximum margin of error, solve the following inequality for n. Z star times our standard deviation formula is less than or equal to margin of error, where p hat is a guessed value for the sample proportion. The margin of error will always be less than or equal to the margin of error if you take the guess p hat to be 0.5. Determine the sample size needed to estimate p within 0.03 with 95% confidence. The critical value is 1.96. Since the company president wants a margin of error no more than 0.03, we need to solve the equation. Multiply both sides by square root n and divide both sides by 0.03. Square both sides. Substitute 0.5 for the sample proportion to find the largest margin of error possible. We round up to 1,068 respondents to ensure the margin of error is no more than 0.03 at 95% confidence. Suppose you want to estimate the P equals true proportion of students at your school that have a tattoo with 95% confidence and margin of error no more than 0.10. Determine how many students should be surveyed to estimate P within 0.10 with 95% confidence. Since we don't have any previous knowledge of the proportion of students, we will use 0.5 to estimate the sample size needed. For 95% confidence interval, we use 1.96, 0.5, 1 minus 0.5 over n, less than or equal to 0.10 for our 10%. Solve for n. Square both sides, bring n to the other side, and then solve for n. We need to survey at least 97 students to estimate the true proportion of students with a tattoo with 95% confidence and a margin of error of at most 0.10. Here's a summary of what we've learned in this section. In the next section, we'll learn how to estimate for a population mean.